All right, ladies and gentlemen, so let's get into it about percent yield. Percent yield is how we assess our experimental prowess or our experimental expertise. This is how we see what we did in lab versus what we did on paper. It's comparing your obtained data, so what you scooped out of your beaker, what you scooped out of your Erlenmeyer flask, what you pulled out of the dehydrator, versus what stoichiometry math tells us is possible. Our goal is to get the lab value as close as possible to the stoichiometric value. Think about it in terms of in real life versus theoretical yields. So the in real life part, that's what's coming from the lab. You actually going through and doing the protocol. The theoretical yield is what we get from the stoichiometry math. And you can basically sum up all types of percent yield from this simple setup. It's your actual over your theoretical times 100 gives you that some number of percent. And that expected yield is your theoretical yield you get from your math. And the actual yield is what you actually scoop up in lab. Any and all variations of percent yield follow that exact same layout. So it's just one process to start to familiarize yourself with. But when we're talking about percent yield, you're addressing your error in a way. So we're all human. We're all made up of parts and pieces that are fallible, which means you can get things wrong. And the act of getting things wrong isn't such a big deal as long as we learn from those mistakes and correct them going forward. So if you get an answer that's less than 100%, that means you've obtained less than the calculated amount. What that means is probably you didn't let the reaction happen for long enough, the conditions weren't right, there was interference of some kind, maybe a temperature variation or what have you. Sometimes you didn't give it enough reactants at a time because you measured wrong, or any number of inputs that a human has to do can make things go less than ideal, which means you produce less product. On the flip side, you can, in theory, get more than 100%, which means you've obtained more than you can calculate, which likely points to some kind of contamination. If you make more than 100% of something, that's not pure substance. That's got something else going on in there. So you have to be careful of making too many mistakes or giving it too much, because then you're not getting the ideal product you want, you're getting something else. And that part of mismeasurement is all encompassed in what's called human error. That's just a part of the lab process. Our goal is to get that human error just as far down as humanly possible. So we just do more practice, and with more practice, we get better at what we do. For general chemistry concepts, you can be asked about percent yield a number of ways, with or without giving yourself the limiting reagents. So if you're not given the limiting reagents or any context about your reaction, you have to go forth and find it out yourself. So we'll see how that plays out. So let's dive into this example here. Determine the percent yield when 36.4 grams of ammonia reacts with excess oxygen if 41.8 grams of nitrous oxide is produced. And I've given you that balanced chemical equation here. But I want you to take a special note of my purple box over here, my pink box. This excess oxygen is important to us. If it says excess, that means we have a plenty. You have plenty of oxygen to go around, which means by default, the ammonia here is the limiting reagent. That puts it at default because the problem told us that this right here is excess. So that part's done for me. So now I get to use what I know about reaction stoke to see how much of this goes into there. So you just set up your normal math like you would. But there's a catch. You must turn your reagents into the same unit and substance as the given. So since I am given grams and grams, I gotta go back to grams. Give it what it's asking for. Give it what it's asking for. So let's start it out. 36.4, ooh, no. Get that out the way. Grams of ammonia here. Turn those grams into moles. So for every there we go. 1 mole of NH3, I'm gonna need to establish that molar mass value. So off to the side here, we're gonna get that inventory going. Pull out that handy dandy calculator. And I'm gonna do it all at once. If that's not your vibe, you feel free to do it the other way and get a number for nitrogen and get a number for hydrogen and run that all together with sigma and have a good old time. You will get the exact same answer and likely have less errors or less opportunity for errors because you're very precise with your numbers. So let's throw that where it belongs. And this molar mass right here will help us get rid of those grams. Now I'm in moles of NH3, so now I get to use those reaction stoke skills and build my molar bridge. Build my molar bridge. I'm asking for this ammonia and this nitrous oxide. Now, what I want you to make sure is that you are dealing with a balanced chemical equation. You must recognize that is it balanced or not. And from what I can tell, I am balanced because 6 times 2 is 12, 4 times 3 is 12, 4 times 1 is 4, 4 times 1 is 4, I got 6, 7, 8, 9, 10 oxygens and 10 oxygens, so I'm good to go. Now, will I always give you a balanced chemical equation? Absolutely not. Those are skills you must perfect before you leave me. So it's okay, just go forth and prosper. But I lucked out. I was given a balanced chemical equation. So now I get to move into my molar bridge as to compare from going from ammonia to nitrous oxide. So I pull out those coefficients here where nitrous oxide's coefficient is right there. I'm gonna slide that where it belongs. And I'm coming from ammonia, so that's right there. So I'm gonna put that where it belongs. No, not with that. Bloop, bloop. There we go. Now I'm sitting in moles of nitrous oxide, so I have to push that through to grams of nitrous oxide because that's what I'm asked for. It's what I'm given here. I'm given 41 grams of nitrous oxide is produced. So I gotta compare grams to grams. So for every one, oh no, do. Yo, what is happening? Stay. Thank you kindly. So for every 1 mole of nitrous oxide, I'm gonna gather that molar mass real quick. What in the... This is not nice, iPad. Come now. that calculator, I'm sure. You get 30.01 grams of nitrous oxide. Now I'm moving into grams of nitrous oxide, so let's see how we go. I'm going to use that fraction function. If you're not familiar with this, don't stress. Just do whole top by whole bottom, and you will get the exact same answer, I promise. And we're going to make 64.1284489.844 grams of nitrous oxide. And how I know it's grams of nitrous oxide because through the magic that is stoichiometry, I see that these units nice and cancel, leaving me in grams of nitrous oxide. Grams of nitrous oxide. That's what stoichiometry tells me I can make. This is the Stochi value. So this falls in the realm of theoretical yield. This is our theoretical yield down here. I'm gonna move these out the way here. We'll keep them handy, because you never know. Just a little bit out the way. Now, I need to know my actual over my theoretical yield times that 100 equals some number of a percent. So here I found my theoretical yield. That's my stoichiometry value. And I'm going to read what was produced in lab. It says if 36.4 grams of ammonia reacts with excess oxygen, if 41.8 grams of nitrous oxide is produced. All right. So I know actually in lab, I isolated 41.8 grams of nitrous oxide. I'm going to compare that to the possible amount I can get from stoichiometry. Notice I was given 3 sig figs a piece in my problem, so I'm good to limit my numbers to 3 significant figures here. 64.1 will do the trick just fine. So I'm going to compare 41.8 over 64.1. That gives me 0.652160, blah, blah, blah. I'm only going to keep 4 significant figures so we understand the point. I'm going to times that by 100 or move that decimal 2 places to the right. And that pushes you into a 65.21% yield. That's a pretty good reaction. But that is too many significant figures. I'm only limited to 3. So let's make that right. Do. All right. That's the premise of it. It's just that easy. But make sure as you're continuing doing your math between your parts and pieces, so like as you're doing this math and this math, it's always handy to have the more decimals, the better. Always save your final bout of rounding to the end so that way you get the best answer choices possible here. At minimum, match your significant figures, but good rule of thumb to get you always the right answer is to keep your number of significant figures using all of them until the very, very end. Now let's get into a little bit more spicy of a situation. So we're asked to determine the percent yield for the reaction if 8.54 grams of sodium react with 5.3 grams of oxygen and 6.35 grams of sodium oxide is recovered. Okay. I don't know nothing about anything, really. I'm not given any context. So no context is given. So now I have to find out. Now I gotta find out. Since I'm not told any context about what's in excess or what's not, I have to go forth and find that out myself. So I'm given 8.45 grams of sodium reacts with 5.3 grams of oxygen. So I'm going to go ahead and step 1, find the limiting reagent. So by using our given values here, 8.45 grams of sodium and 5.3 grams of oxygen, I'm going to move each of those into what we're given here as a product. I only got one product to choose from, so that limits my choices. Okay, cool with me. So I'm given grams, I'm gonna move into moles. Grab my handy reference sheet to grab the molar mass of sodium. I'm gonna do the same thing quickly down here for the masses of oxygen. Remember oxygen being that diatom, so we gotta use that diatomic mass because it is indeed solo here, so we have to recognize that as a diatom. It's a diatom. All right, so now I'm sitting in moles of both. I'm gonna start building my molar bridges. So now I'm moving from moles of sodium to moles of that sodium oxide here. Same thing here. Let me move this out the way. I'm just setting them both up at the same time. You don't have to. Just keep it one at a time if that floats your boat. Live your best life. So now I gotta pull my molar ratio, and I get that from these coefficients, or imaginary ones, if there's nothing there. So in front of Na2O2, I have a 1 coefficient, and that comes from right over here. Is that molar ratio of Na2O2. Same applies to this mole of sodium over here. That's that coefficient of 2. And then we're just gonna move that into, we're in moles of sodium oxide. However, comma, we were given grams as a recovered product, so we must move back into grams. So for every 1 mole of Na2O2, I have a certain number of grams coming from that molar mass value. We get, so up here, I'll squeeze it in here. We get 2 of those, 22.99. And then 16, of course, since it's in a compound, get to use it just like it's meant to be. Yeah. Well, not meant to be, but the simple version. Get a whopping 77.98 grams. Let's keep that pushing. 77.98 grams of Na2O2. All right. So I'm sitting in grams of what I'm asked for so I can stop working. Now I'm going to do the same thing down here for oxygen. I'm at the building the bridge part. So I'm going to slither my way over to make a bridge. I see a coefficient of 1 in front of my oxygen and a similar value in front of that NaO2, Na2O2. So go ahead and drop that down as a 1 and 1. So I'm sitting in moles of sodium oxide. So for every 1 mole of Na2O2, I got that same molar mass we just calculated. Now I'm going to run some math. I'm going to use the fancy fraction option. If you're not familiar with that, don't stress yourself out. Whole top over whole bottom works every single time. Notice how I've keyed everything in. We're going to keep a hold of those decimals for later. I'm going to write a few. That's what the dot, dot, dot stands for, really. Grams, I'm in grams of Na2O2. Now let's do the same thing over here. Move that out the way. Hit that fraction again. Times 1 times 1 times that 77.98. Here down here, I'm going to use that diatomic mass times 1 times 1. Gives me that 12. Blah, 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 blah. I'm going to write all that. Nah. Grams of Na2O2. Now, what we can do is find the limiting reagent. I have a comparison of 14.33 and change and 12.15 and change. Who is my limiting reagent? Pause the video and work that out for yourself. But indeed, this one is the smallest, so that makes oxygen my limiting reagent. So since oxygen limits the reaction, I can only produce, by stoichiometry, the 12.915 and change grams of sodium oxide. Now, the problem told me I got 6.35 out. So it's actual over theoretical times 100 to give you some number of a percent. So I'm only going to use the limiting reagents values. So that actual came from the problem. 6.35 grams of Na2O2 over the theoretical one of 12.915 and change grams of Na2O2. So 6.35 over, recall that down, I get a whopping 0.49165 blah blah blah. Times that by a not 400. Bloop bloop. Bloop bloop. I move that decimal over twice. You get 49.165969019.6% yield. Let's get that calculator out of the way and see how many sig figs we're given. I see 2 here, I see 3 here. I should be reporting in 2 significant figures. So you're roughly dealing with a 49% yield. So that will give you, determine the percent yield for the reaction. You will have 49% yield with that perceived value. Easy, breezy, beautiful. Have a girl. But that is everything I have for percent yield. It's a pretty straightforward process that always follows this same setup of actual over theoretical times 100 to give you some number of a percent. Now, just pay attention to the details you're given in the equation or in the problem. That way you don't have to do double the work and you can make sure to answer the question. We have to make sure we're answering the question. Because here, it got a little spicy because you weren't given any context. So you had to go forth and find it yourself. So make sure we're paying attention to the details we're given in the question so we can answer it appropriately. So you pick whatever your lesser grammage is because that's what limits. That's where we have to move from. Well, that's everything I got for you for percent yield. Go forth and prosper. If you have questions, send me an email. I'm happy to help where I can. Until next time.